You just go over there.
Okay, guys, let's get started. Got a lot to cover today. Hopefully, you've been working on this here. Simple additions to carbonyls. Is there a leaving group present? If not, we're not going to eliminate anything. We did 1 and 2, correct? Number 3. Did we do number 3? What's the nucleophile? Essentially the carbanion, the benzene anion. Nucleophiles add to carbonyls. These electrons add to carbonyl, electrons up. Boom, 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 electrons up, becomes minus. Now the phenyl bond is there. There's also an H there, yeah?
Yeah.
I'm not going to draw it in. Okay, can we reform carbonyl and kick off a phenyl, an H, or a propyl?
No.
No, you cannot. This is just a simple addition. This is standard chemistry for aldehydes and ketones. There's no leaving group like an OR or chlorine or even nitrogen which can leave. These things cannot leave. Only thing you can do, game over. All you can do is put a proton on. Now with sodium borohydride, you can use a protic solvent and the solvent will supply the proton. You cannot use a protic solvent with LAH or a Grignard. With these, the workup has to come later. You add in your favorite acid, H plus workup, and you get your product just by putting the H on. I'll draw it sort of boom, boom, boom. OH, phenyl. There's your product. Just a simple addition of nucleophile to the aldehyde, and then the O minus picks up an H upon workup. It's called a simple addition. We didn't do an addition and elimination. There was nothing to eliminate. Nothing to eliminate with aldehydes and ketones. Usually. Remember back with epoxides, what do you get when you react nucleophile with an epoxide? What product? Nucleophile, carbon, OH? Okay. In these three, what you get was what? What was the nucleophile? Phenyl. Nucleophile, carbon, OH. Okay? Nucleophile, carbon, OH. Because the COH used to be what? It used to be carbonyl. The nucleophile came in, okay, and you made that bond. Nucleophile, and then this picks up an H. Nucleophile carbon OH. That's what all three of these first ones were. Except up here, what was the nucleophile? It's actually H minus. Again, most of this, you can't memorize every single reaction. You have to learn just basic, what's a nucleophile, carbonyl, do your mechanism. Hey, there's your product. If you think like that, you're going to have a better time when we get to test 4, because there's going to be a lot of reactions in carbonyl chemistry. It's just like learning math or reading. You don't memorize every word, you just learn how to read. Sound them out. Okay. Let's do a little on the right here. For number 1, what reagent would convert product back to starting material? What was the product? It was boom, boom. It was that, right? Because there was a new H came in, electrons up. Here's the new H, you see it? Electrons up, that picked up an H. How would you convert this back? That's what the question over there asks. What's going on when we convert it back? What functional group is that, Warren? Alcohol, okay? Alcohol to the ketone, have we ever done that? Yeah. That's the oxidation of the alcohol. How would you do that? Nick already said it, one of the big 3, right? Big 3 oxidants. KMNO4, sodium dichromate. Right? So backwards is oxidation. What do you want to call forward?
Reduction.
Yes, that's reduction. And usually when you add H's, which that's what we're doing with a hydride, right? When you add H's, that's reduction. What you have here is the classical cycle of carbonyl being reduced to the alcohol and then back and forth. Okay? Oxidation-reduction. So the oxidation was covered during test 1. This is a reduction. Maybe you add H's here. Everybody's using sodium borhydride in labs. Very convenient reagent developed by H.C. Brown in the 1950s. He won a Nobel Prize in 1979, essentially for developing that reagent. Easily to supply hydride. Let's look at this cycle here. This would be called a redox cycle, right? Because you're doing reduction oxidation. It's a redox cycle. Where do you see that at? Well, lots of places. One place you see it as you turn over. Estradiol, estrogen, and estrogen. So diol implies it's got two OH groups, right? Okay. But in the body, particularly female body, this OH here can be oxidized to the ketone. Now, your body doesn't use like KMNO4, your body uses nice enzymes. Okay? That would be, that's called estrone. It's another estrogen, type of estrogen. But then you can go back to estradiol by reducing this. Essentially, when you reduce it, you have an H here and an H here. But we do that with like hydride reagents. By the hydride, in lab we do it. Hydride reagent, which supplies this, right? Adding the carbonyl electrons up, and then the O minus picking up an H from protic solvent, or you add in some acid. Now your body has a hydride reagent. Not these. Your body has NADH. You ever covered these?
Yeah.
Nicotinamide, adenine, dinucleotide. But this is NADH. It's got the H. There's the H. This is your body's hydride source. And when it gives up the hydride, it forms NAD+. Now, how does it give up the hydride? Note that NAD+ has what type of ring?
Pyridine.
It's protonated pyridine, more generically aromatic ring. Now, how does this shoot off a hydride? These electrons move here. These electrons move here. And it shoots off the H and the two electrons. Why would it want to shoot those off? Shoot that H minus off? Because it becomes...
Anti-aromatic.
No, that's not that's aromatic. 6 pi electrons. 2, 4, 6. Just because it has a positive charge doesn't mean anything. It's 6p orbital, 6 pi electrons. Shoots off the hydride to become aromatic. Okay? But it has a positive charge, so the hydride likes to come back in and move the electrons back up. Really, it goes back and forth. Okay? But NADH is your body's hydride source. There's some things on here. I don't want to take the time right now. Please look at that. We'll see. We may come back to it if we have a little time. Please look at that. Let's go back to our reactions. Questions on the right? For number 2, what reagent would convert product back to starting material?
PCC.
What was the product? Boom, boom, boom. It was primary alcohol, right?
Always.
Yeah, would you want to use big 3 here?
No.
No, because the big 3 we convert it all the way to the carboxylic acid. So what do we want to use?
PCC.
PCC?
Yeah.
Yeah, it's that, remember that? So that's a little bit of review. Going backwards to the carbonyl. Here, going forwards. For number 1 and 3, is product R or S? Huh? What was the product of 3? It was, don't we have it? We erased it. Boom, boom, boom. Wasn't that the product of 3? Where we made this bond, nucleophile carbon-OH. Not carbon-carbon-OH like epoxides do. Okay, it's product R or S.
Both.
Well, you do see it's chiral here.
Yeah.
Is it R or S? Somebody said both. Anybody else? Why is it both? Well, this is not chiral. This is not optically active. So your product can't be. You can't just create, all of a sudden have R, which would be optically active. You can't create optical activity from nothing. Yes, it's racemic. Why is it racemic? Because when the nucleophile attacks, that carbon becomes tetrahedral. Okay? It's now tetrahedral, right? The carbonyl is here. When the nucleophile attacks, it doesn't come straight up here and the O goes up. It's more the nucleophile attacks from the front or back. Okay? If the nucleophile attacks from the front, what are you going to get? The phenyl would be forward, and the OH would be back. Now that's sort of an ugly bond angle. You clean that up. If you really want to draw it, it'd be a better bond angle to draw it like this. And then draw, what else is here? Just an H, right? This is where the phenyl attacks the carbonyl from the front and moves the oxygen back. But you can also attack from the back and move the oxygen forward. So that's how you would get both enantiomers, and you would get a 50-50 because it's just as likely to attack either side of that planar carbonyl. Okay? So just a little bit of review over there. Going backwards. Show 3 different reactions that you could use to make this compound. Starting with a carbonyl, underline, any carbonyl compound, show a reaction. Now just show any carbonyl compound, and then show a reaction of that carbonyl compound that would give that. Keeping in mind, nucleophile carbon-OH. Take a minute to do that. And amongst everybody, hopefully we'll get all 3 possibilities. Okay. Carbon OH, nucleophile carbon OH. We can envision making that by reacting phenyl anion with I'll draw on the H of my aldehydes. That plus that would give that after H plus workup, right? Well, this we need to give a precise reagent. This would be like phenyl magnesium bromide. Okay? So the phenyl anion adds electrons up. That gives this with just minus. And then the minus picks up a proton from when you add in your favorite acid. Well, we could have also have made this bond over here by reacting what would be here? Benzaldehyde with what? CH3 magnesium iodide or something. Bring in the methyl anion electrons up. Of course, that requires H plus workup. What's the third way we could make this from a carbonyl compound? The methyl ketone, which is called acetophenone, reacts it with what? There's an H here, right? We can make that bond. Sodium borohydride, or what? Or LAH. If you use sodium borohydride, you can use a protic solvent, and that'll supply the proton. If you use LAH, you can't use a protic solvent. You'll start a fire. You have to supply the proton after it reacts. So that's 3 different reactions starting with carbonyl compounds. Question?
For the one reacting with benzaldehyde, do you need an H plus workup there as well?
You need H plus workup for all of them except for the sodium borohydride, which if you use that, you could use like ethanol solvent. And the protic solvent would supply the H. Essentially, all these require H plus workup. Strong anions like Grignards and hydride, you can't have alcohol around because it'll just take the H from the alcohol. Sodium borohydride is an exception. That's why it's so versatile. It's mild enough that it won't be so eager to react, but it will react. Remember, in lab, you're reducing your imine with sodium borohydride. You're using what solvent? One propanol, yes. The protic solvent, okay? You can't use LEH with 1-propanol, you start a fire. Add LEH to 1-propanol, you better stand back. The H minus will take an H, create hydrogen, but it'll be so exothermic that it will ignite. Just like when we put sodium in water, if we did that. Okay? LEH is known for starting fires. It's very moisture sensitive. Okay, let's move down here. What do you get in? Oh, acid chloride. What do you get if you react that with LEH? It will not be carboxylic acid. We don't have an oxygen nucleophile. H minus, these electrons add, electrons up. I'll draw in the H, right? There's a new H. Lipophilic addition. Okay, is this thing going to just sit there?
No.
We have a leaving group.
It won't listen to you.
It won't. It'll reform the pi bond, kick off the leaving group. Anytime you make a pi bond with a lone pair, kick off the leaving group, it's easy to do, right? But you're not going to kick off a R group or an H. See, here we got an acid derivative with a leaving group. What's that going to give? Aldehyde. What happens next? H minus adds to the aldehyde, and you're going to get, after H plus workup, this means there's another step, that's H plus workup. We're going to get
Alcohol.
1, 2, 1, 2, boom.
So there's no way to stop at the aldehyde.
Because you need to get rid of aldehyde.
Okay, good question. With LAH, you keep adding until you can't add any more. There's no way to stop at the aldehyde. Okay? Try to stop at the aldehyde, you're just going to get mixtures of aldehyde and alcohol. You have to go all the way to the end. Okay? The aldehydes form first. Not isolated. We can put brackets around it. It's not isolated. We get further reduction. Hopefully everybody understands this. I know a number of you just don't see what's going on here. Hopefully by the time the test comes, you will have sat down and just did the mechanism. And after you do the mechanism, show your product. And then look at your product and see how it's the same as what I'm doing on the end. After H plus workup. If you can't do that, then... Okay. Dibol. If you want to stop with the aldehyde, you can do it, but not with LAH. You can do it with Dibol H. Dibol H stops at aldehyde. Now see, I hate to write that because then you're going to say, what does Dibol H do? And you're going to say, well, it gives an aldehyde. No, it gives an aldehyde in this case. Dibol H will only add once. Basically, the product here in this case is that aldehyde. What is Dibol H? Well, first off, it is a hydride source. It is also an aluminum. That's what the aluminum is. Di stands for 2. B stands for what?
Boron.
No, it's not a boron. It's a butyl, but actually it's isobutyl. So it's the D stands for di. The IB must be isobutyl. What we got here is 2 isobutyl groups on the aluminum. Diisobutyl aluminum hydride. Now, compare that to LAH. Tell me 2 differences.
Charge.
There's only one hydrogen.
Yes, that's the difference. You answered the question. You weren't reading my mind, though. I don't know why you wouldn't read my mind. LAH, the aluminum is negative. The aluminum is mad because it doesn't like being negative. Strong hydride source. Dibol is actually a neutral aluminum. So the aluminum is not as eager to kick that hydride off. Not as reactive towards. Okay? This is a less reactive hydride source. First, it's not charged. Tell me another reason it's less reactive. Sterics. Okay? Now when we say it kicks off the hydride, it doesn't just kick it off and then the hydride sort of floats around until it finds something to react with. This actually sort of approaches the reagent and then it sort of kicks it off. This is going to be more difficult to approach the carbonyl. Why? Got these big bulky wings on it. Okay? So sterics and less charged, it's less reactive hydride source. Also, if you do it at very cold temperature, why minus 78? Why not minus 72? Minus 78 is the temperature you get when you add dries to acetone. Okay? It's not a random number. It's you add dries to acetone. It's like 0 degrees. It's what you get when you add wet ice to water. Okay? So it's not just a random number. It's dry as acetone temperature. Real cold. Don't stick your finger in it. You can keep it controlled, and it will only add once, and you can get a pretty good yield of the aldehyde using dibol H. There's a number of hindered hydride sources or less reactive hydride sources. Your book may show others. Dibol H is sort of the one that I showed. Yes.
So just because it adds once, if you were to use dibol H in the example above, it would just give you just the standard alcohol?
And number 4?
No, like an example 3 and 2 up there. So if you were to use dibol H, it would just give you the, it would be the same thing.
Oh, up here?
Yeah.
I reckon so. You would never do that because dibol H is way more expensive than those.
Yeah.
But theoretically, I reckon it would. I don't. There's sometimes we'd have to look. There's a note at the bottom. Some of these hindered things only react with like acid chlorides. But in general, yes. Your answer, yeah. Okay. How about number 6? What if instead of a hydride you use a Grignard, which we know is an R minus, alkyl, or like a phenyl minus? Okay, here's this. Just like LAH, Grignards keep adding until you can't add again. So essentially it's going to add twice. What's the intermediate, and then what's the final product? And you get the same outcome whether you use like an ethyl Grignard or ethyl lithium. These are going to add twice. Got the ethyl magnesium iodide, so it's anion adds, electrons up. What then happens? Electrons back down, kick off the chlorine. I'm just going to do this sort of quickly, mechanistically. Boom, 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 boom. So what do we get? It's actually a ketone. When that ethyl replaces the chlorine by a nucleophilic acyl substitution reaction. Does it stop at the ketone, or can a Grignard add to the ketone? Yes, it will add again. Electrons up. We get we have 2 of the same R groups now, 2 ethyls. And now what? Is this going to come back down and kick something off? No, it's game over. What can you do here? Just add in your H plus workup, and that's going to be an OH, right? So what type of product did we make? It's actually a tertiary alcohol. Okay? I think below we're going to start using esters. Yes, if this was like an ester, you'd get the same product. It just wouldn't be as reactive as the acid chloride at the beginning. Grignards add twice. Keep adding. Hydride, standard hydrides add twice. Reaction 3 would get the same product with an ester. Okay? The ester, your O-ethyl or your O-R group would be the leader to give your ketone, and then you add to the ketone again. So, acid derivatives will have a leading group. When you add to them, You can then reform carbonyl and kick off that leaving group. Aldehydes and ketones don't have a leaving group. What if you want to stop at the ketone? Can you do it? Well, somebody along the line said, hey, I want to stop at the ketone. I don't want it to add twice. And chemists developed a reagent. This here. Have we seen cuprates before? I don't think so. It's called an organocuprate. Cuprate. It is organic, organocuprate. Now these do not react with ester. Right? But acid chlorides, they will. What is the structure of a cuprate? It's a copper, lithium. Okay. Lithium is always what charge? That means the 2-ethyl in copper is what totally? Yes. It's a copper with 2 R groups. This case it's ethyl. And what's the charge of the copper? Minus. And then you got your lithium plus. Now copper doesn't like being minus. Actually, in Gen Chem, you probably would get points deducted if you said it was ever minus. But it can't be. There's a minus. Copper's usually plus, okay? Now, copper doesn't like being minus, so what does it say? R group, you and your 2 electrons take a hike. So it will shoot off the R minus, okay? R and 2 electrons, R and 2 electrons, and that happens to be minus, okay? So it's a, so now it goes to why the boron minus shoots off H minus, okay? It's called an organocuprate reagent. How do you make organocuprates? How do you make such? You take an organolithium or Grignard. You basically need our minus source. This could be a Grignard. And you react this with copper, trying to show this on the handout? I don't think so. You react this with like copper bromide. To balance this, you need 2 of these. And see, this is copper plus, right? Br minus. If you add 1 R group to the copper, you get copper with an R, and the copper would then be neutral. If you add another R group, basically the copper plus now has 2 extra electrons because it owns 1 of these and it owns 1 of those. If you give this 2 extra electrons, it goes neutral and then it goes minus. See, this is now minus. What's left over? Lithium bromide. Okay? This can be a Grignard here, okay? Now this, if you reacted with this, it add twice. But if you first form your cuprate, the cuprate will only add once. Now, I'm not going to try to explain why it only add once. It implies that it's less reactive than your alkyl lithiums or your Grignards. But what does this give?
Ketone.
Yes, it's going to give that ketone that we had in brackets. And this is actually a great way to make ketones. From smaller fragments. Okay, this is a 5-carbon fragment. We now have a 7-carbon ketone. The only other way we've seen to make ketones, I believe, is take this alcohol, oxidize it, right? That would get the ketone. See, the difference is, here you're combining two carbon fragments. Where here, you're not combining carbon fragments, so you had to build this up another way. Here you can build your molecule larger with two different reagents. Okay, cuprates only react with acid chlorides. That's what this note says here. That again implies that your cuprates are less reactive. They only react with the more reactive acid chloride. Very good reagent to make ketones. Called a Gilman reagent. Your organocuprates are also called Gilman reagents. Usually if something has a name like that, it's usually a very important reaction. I'm worried that it may not be chapter 20. Because I can't remember if I checked this or not. I know at one point it was wrong, and I can't remember. But every book should have an index. And if you look up organocuprates, you'll find that. What do you get if you react a amide with LEH? Show the product. What do you get first? What's the intermediate? Somebody said aldehyde. What was said over here? It's like somebody said anion or something. What'd y'all say over here, Sadi? Nobody said anything?
I thought it was anion.
What was it?
I said anion.
Oh, it must have come around this way. So what's the nucleophile? H minus, electrons add, electrons up. What do we get? Electrons up. Nucleophilic addition, yeah. What's next? Electrons down, kick off the nitrogen. Seems very reasonable. But you'd be wrong in this case. What's the product here? The product here is it's primary amine. How does this happen and why? Yes, seems very reasonable to bring these down and kick off the nitrogen. But is nitrogen a good leaving group?
No.
No. Now we've said it can leave. I mean, you can hydrolyze an amide to a carboxylic acid. It can leave. But apparently it doesn't because it's not going in the product. What leaves this carbon? Not the nitrogen. The oxygen actually leaves. See, what happens is these electrons, when they come back down, that nitrogen says, hold on, I'm not going to leave in this case. What else is going on? Well, how can we get this oxygen to leave?
Nitrogen electrons go in.
How do you make oxygen a better leaving group? Do we have any acid?
No.
No, if you have acid, you'll have fire, because you can't react H minus with H plus. What is here other than H minus? ALH3. And ALH LH3 is similar to like AlCl3. What did we use this for before? Carbonyl Lewis acid. This complex with the aluminum. This is the proposed mechanism right now. Then we can get OLA, aluminum, H3. What's the charge in aluminum now? Back to minus. It doesn't, okay. Have you ever seen aluminum minus?
No.
Sure, right here it's aluminum minus. Then you have NH2, H. Does it make sense that this would have complex to the aluminum?
Sure.
I mean, way back when, didn't we complex this with the aluminum when we did Frito crabs? And this is not even really a basic atom. That's a pretty basic atom right there. Now the nitrogen says, ha ha, I'm going to come in and kick you off. And that gives, I'm going to draw the H up now because it's just a better bond angle. And H2 plus the oxygen Now I'm gonna lie to you because otherwise it would take 15 minutes to explain this, and I don't know that it's working. But I'm gonna do what most books do. Okay. How can we get home from here? Do you think this aluminum wants to get rid of something? Yes. It shoots off another H minus. See, actually, all four of these can eventually be shot off because as you keep making aluminum minus, it keeps shooting these off. And if we shoot these off, where can this go? And move these here. This is like a protonated carbonyl, right? If you drew that as an oxygen, as a carbonyl, and if you had an H on it and made it positive, don't nucleophiles add to carbonyl, especially when they're protonated? Yeah. It's like a protonated carbonyl except it's a nitrogen. If we add in the H minus here, okay, this is H and the 2 electrons, okay? It's H minus. What does this give? Give the final product. See, the nitrogen's reluctant to leave, and so this doesn't come down so fast, and that doesn't get kicked off so quickly. Even though we say you can make a pi bond, in this particular case, we actually make the amine. It's actually a deoxygenation reaction. Okay? Now, you can have R groups on the nitrogen. It doesn't just have to be a primary answer. So once you see the mechanism, does it make pretty much mechanistic sense? Do we do anything wickedly odd there? I mean, back in Gen Chem 1, you learned the definition of a Lewis acid. Except what? Except for electrons. What's it doing right here? Okay. Of course, way back then, you didn't have any, what do you mean, except electrons? Okay. Now that you're more experienced, you sort of, okay, that makes sense. Right? Okay, how about nitriles? I'm not going to cover LAH, I don't think. But you also get the same product. Either one of these gives the same product. You also get it with H2 and catalyst. And it's just like an alkyne. Alkyne is C triple bond C. This is C triple bond N. What do you get when you hydrogenate a C triple bond C? What if we reduce this with H2 and like palladium? Get butane. Not double bond. If you want to stop it at the alkene, what do you have to use? Poison catalyst. Or that would be cis or transalkene. Poison catalyst with hydrogen would get cis. What if you don't use a poison catalyst? You add two H's and then you add two H's again. Same thing here. So what's the product? If you add two H's to the CN and then add two H's again, what's the product?
Primary amines.
Yes, primary amine. The CN used to be triple bond, but now it's CH2 NH2. These two carbons used to be triple bond, but now it's CH2 CH2. Okay? Nitriles can be hydrogenated down to the single bond system, which is a primary amine, just like alkynes. Now LAH will also do this, and I'm not going to go over that mechanism.
Is it pretty much the same thing as that?
It's what?
Is it pretty much working the same way?
You could be able to do it on your own. You do need to kind of use the aluminum Lewis acid to keep from having a 2 minus. It basically hydrolyzes twice, and then the nitrogen has to pick up H's from workup. You would have to have an aqueous workup there. Where down here, this is not an ionic mechanism. This is where you shoot the H's in like darts. 2 H's and then 2 H's again. Okay? That's your old classical hydrogenation, just like alkyne. All you got to do is look back at your alkyne. All you got to do is look at this and then change this atom to nitrogen. It's the same thing. Okay. Some predicted products down below. Hope you just look at those. It should be pretty straightforward. Let's look at the one on the front. Do that. Okay. We're about a half a lecture behind. I hate to rush towards test on Monday. What do you think about delaying until Wednesday? Okay, test on Wednesday. I think we rushed a little bit too much. On Monday, we'll see what type of questions are out there. I want to go over a few little miscellaneous things. On Monday, we will also start test 4 material. Okay? I think this is best. I don't want to rush into the test. No time to answer questions here. We're out of time today. Okay? The first 15 minutes of Monday, we'll see what type of questions there are. Lab next week is last week. Next week you'll be turning in compounds, etc. Next week is the end. You'll turn in your compounds next week. That report is due after